In this lecture, I will discuss the topics in reliability. The main topics are reliability, maintainability, and availability. So, what do we mean by reliability? So, if a component or a system it's put into work at initial times is 0 and it fails after a time, say capital T, then that capital T is called the time to failure. Okay, so in it's called the life length of that component or system. So the reliability basically gives the probability that the component does not fail in the interval we are taking. So if you are taking a time t, small t, in that interval, what is the probability that the component or system is not failing? So if capital T is the life length of the product, basically the capital T greater than small t, right? So in that case, we will be having a positive, we will be having a non-zero probability, right, of the component not failing, right? So the time to failure or the life length is, it's a time, right? So it will be always greater than or equal to 0, and it's a random variable which is continuous. Okay, so the probability density function of that random variable, suppose it is f of t, f of small t, right? So capital T equal to small t, that probability is given by this f of t. Okay, then the reliability is basically the probability that the life length is greater than the chosen time small t, right? The time to failure is greater than the chosen time small t. What is the probability of that? That probability is the reliability for that small t. So this is a cumulative probability, and or this is a like sum of probabilities or integral of probabilities. And what is that? Using complementary law, this is equal to your 1 minus probability of t less than or equal to t. Now this is nothing but the cumulative probability, capital F of t, right? So 1 minus capital F of t, where capital F of t is a cumulative probability up to small t. So it is integral minus infinity to t f of t dt, but since the random variable is starting at 0, capital T is starting at 0, right? So it's not taking negative values, it's a time, right? So 0 to integral 0 to t f of t dt, that is your capital F of t, which is a cumulative probability function of the random variable capital T. Okay, now your reliability is basically 1 minus cumulative probability function of t, right? So so reliability is also a probability basically. So probability of the time to failure is greater than t. Okay, so it only takes values from 0 to 1 again, right? So now using this idea, that is reliability is 1 minus cumulative probability function of the random variable t, we can rewrite it as this is capital F of t is, since it is integral 0 to t, instead of f of t dt, you should be using f of u, a dummy variable, f of u du. In that case, your reliability now has the form 1 minus integral 0 to t f of u du, right? So that we know that the total integral is 1, right? And what is the total integral? Total integral, or this 1 is basically integral, it's a total integral, right? So it is integral 0 to infinity f of u du, the total integral of the distribution function. So this minus integral 0 to t. So it's basically integral 0 to infinity f of u du is integral 0 to t plus integral t to infinity, and that integral 0 to t is getting cancelled, and what remains is integral t to infinity f of t dt. Otherwise we can use this basic definition itself to get that. So the reliability is basically the probability that the time to failure is greater than the small t, right? Reliability at a point t is the probability that the time to failure is greater than the small t. Now that probability is integral t to infinity of the density function. What is the density function f of t? So that way also you can get it. So reliability, it is this integral. It's not f of t dt, it's f of u du. Integral t to infinity f of u du. Now what is now if you integrate using basically, if you take the differential on both sides, basically it is your fundamental theorem of calculus, application of fundamental theorem of calculus. Take, so this r of t, it is this integral. In that case, once you take the derivative, this the concept of differential is the inverse operation of integral, that comes into picture, and if you take the derivative, you will be getting derivative of 1 is 0, and integral 0 to t f of u du. So it will be f of t minus f of 0. And what is f of 0? So here it will be f of t minus f of 0 by fundamental theorem of calculus, right? So this minus is there. Now what is f of 0? F of 0 is basically the probability of the time to failure is 0. So for any component that is at least it will stay more than 0 is assumed, and this part f of 0 is assumed as 0. This probability is assumed as 0. So the capital T is basically assumed to be greater than 0. Okay. Capital T takes the value 0, and for that in practical sense, that is assumed to be having probability 0. So any product or component loves a non-zero time. The time to failure is non-zero. Okay. So now what is this? This is nothing but minus f of t. So you are having f of t is, so this is your r dash t. So your f of t is basically negative of r dash t, right? So so your probability distribution function of the time to failure, it is the negative of derivative of reliability function. That relation we are getting here. Now there is a concept called hazard function. It's also called instantaneous failure rate function. So rate of failure is, instantaneous rate of failure is given by this. So it's defined as, it's denoted by lambda of t, and it's defined as the density function to the reliability function ratio. Both are probability functions. So f of t by r of t, that is called the hazard function. Okay. So since f of t is minus r dash t, you can rewrite it as minus r dash t by r of t. Now you will be getting a differential equation here. So this implies from this equality you will be getting r of, or you can so you can take the integral on both sides basically, and you will be having integral of say 0 to t. If you are taking integral 0 to t lambda of t, you are integrating, so dummy variable, let's use lambda of u du equals integral 0 to t minus r dash u, dummy variable, divided by r of u du. Now r of u, its derivative is r dash u du, so that is there. So this integral becomes what? This becomes there is a minus here, let's take that minus to the other side. So minus integral 0 to t lambda of u du is integral 0 to t, so r of u you substitute as say v, then 1 by v dv, it will be becoming, that minus went to the other side. So you are basically having so the derivative of a reciprocal function, right? So that's what you are having. So and that is nothing but log. So log of r of u, it becomes, once you integrate, because the derivative is there, you're multiplying 1 by r of u with derivative of r of u, right? So you are having the integral is basically log of r of u with the limit 0 to t. This becomes what? Log of r of t minus r of 0, reliability at 0. What's the reliability at 0? The the probability that the product lasts more than this time, 0 time, that is assumed to be 1, right? So the r of 0 will be 1, so you'll be having log of r of t minus 1. Now yeah, sorry, there is a mistake here. It's not log of, it's log of r of t from 0 to t, so log of r of t minus log of r of 0, so there is a mistake here. So this minus log of r of 0, okay, minus log of r of 0. Now r of 0 is 1, as I explained before, so log of r of t minus log 1 is 0, so that part is not there, so it's log of r of t. Now take the exponential out on both sides, you will be getting, make the right side now left side, so exponential log r of t is nothing but r of t equals exponential of minus integral 0 to t lambda u du. So this is what you get, right? So this is your r of t, that's what's given here. So r of t is nothing but e raised to minus integral 0 to t r lambda of u du. And what is your f of t? F of t is the derivative of this thing, right? So now once you take the derivative, what happens? So r dash t is your f of t, so f of t is r dash t, this we know, minus r dash t, it's not r dash t, it's minus of r dash t. So what is that? With respect to t, we are taking the derivative of this thing, right? So minus of e raised to something, its derivative is itself into whatever is inside, right? So e raised to minus integral 0 to t lambda of u du into the derivative of this part, integral 0 to t lambda of u du. What is that? Again, fundamental theorem of calculus comes there. So it will be lambda of t minus lambda of 0. The derivative of integral 0 to t lambda of u du will be lambda of t minus lambda of 0. And what is that? Lambda of 0 is again 0. Why? Because f of 0 is 0 and r of 0 is 1, you will be having lambda of 0 is 0. So here you will be having just lambda of t minus 0, or it is into lambda of t. And there is a minus, this minus is coming there, so into minus lambda t basically. So and that minus and minus cancel, or it becomes plus, and you will be getting lambda of t into e raised to minus integral 0 to t lambda of u du is your probability density function of time to failure. F of t is the probability density function of time to failure. So that formula also will be getting f of t is lambda of t e raised to minus integral 0 to t lambda of t dt, where lambda of t is the hazard function defined as f of t by r of t, or minus r dash t by r of t. Okay, so using hazard function you can write the reliability as well as the density function. Okay, hazard function is a ratio of density function to the reliability function. Now we have the mean time to failure. What do you mean by mean time to failure? Failure random variable you are having, time to failure random variable we are having, which is t. So what is the mean time to failure? It's the mean of that random variable, so it's expectation of that random variable t. So what is it? It's density function. T has the density function f of t, right? F of small t, right? So capital T is the time to failure. So for that random variable, what are the possible values, right? It's any time. Now the probability function of that random variable is f of t. So what is the expectation of t? It becomes integral 0 to integral minus infinity to infinity t into f of t dt, but minus infinity to 0, the probability is 0, so that the integral starts from 0. 0 to infinity t f of t dt is your expectation of the time to failure random variable capital T. Now okay, so now this is equivalently you can write integral 0 to infinity r of t dt as well. Okay, so the reason behind that is you can rewrite Yeah, so r of t, so you have f of t is nothing but minus r dash t. Just substitute that and take integral, you will be getting this result. So this becomes equal 0 to infinity t into minus r dash t, so minus I'm keeping outside, minus r dash t dt. So here we are not using the dummy variable because the limits are limit you don't have t. So what is this? What is this integral? We can use integration by parts, keeping t as the first variable or first function. So what is that? Integral 0 to infinity, this integral we have, so minus is outside, so first function into the integral of the second, which is r of t, right? So from 0 to infinity minus integral 0 to infinity of the derivative of the first function is t, so 1 into integral of the second, which is r of t, right? So this is the integral now. So at t equal t goes to infinity, r of t, the reliability goes to 0 faster than t goes to infinity. R of t goes to 0. So for that reason this t into r of t goes to 0. The product itself goes to 0. And when t equal to 0, r of t is 1 and t into r of t becomes 0. So this part gives you 0 only. So minus of minus will be plus, and you will be getting the mean time to failure equivalently is integral 0 to infinity r of t dt. So this is how this result is coming. So mean time to failure, by the definition of mean or expectation, it is integral 0 to t into f of t dt, and that equivalently gives you, using reliability, what is the mean time to failure. It is integral 0 to infinity r of t dt. So it's the integral, total integral of the reliability function is the mean time to failure. Okay, mean of the time to failure random variable, it is the total integral of reliability function. And minus infinity to 0, it is not there, time is not taking any values from minus infinity to 0. It starts at 0 actually, right? Now the variance of time to failure can also denote it as sigma t square by, if we are using this definition, it's expectation of the random variable t minus expectation of t whole square, right? Or equivalently it is expectation of t square minus expectation of t the whole square. You will be having correspondingly you can have two formulas or two representations for variance of t. So integral 0 to infinity, so expectation of t square is integral 0 to infinity t square into f of t dt minus expectation of t is nothing but the mean time to failure. So using that you can write it as mean time to failure whole square. So variance can take this form also. Means this representation gives you the variance of the time to failure, or using t minus expectation of t whole square, its expectation, you can have an equivalent form. Okay, so it is t into so instead of t you are using t minus expectation of t, so it becomes t minus mttf, the probability function of that, into t, its integral also. So there's a square also, right? So yeah, instead of t you are using t minus expectation of t whole square as a random variable, right? So now for that random variable, what is the corresponding integral that's going to, so that integral also gives you the variance. Okay, now we have conditional reliability of a system or component. That is, you are having a warranty period, or it's also called burn-in period or wear-in period. Now after that warranty period, what is the reliability of the product? So that is basically a conditional probability only. So reliability of the product, or R of the reliability of the product for time t, given that t naught is the warranty period. So it will last for t naught period is assumed. So now what is the probability that it lasts more than the given time small t? So that will be represented as a conditional probability, and it is not denoted like this: reliability of t given t naught. So t naught, it will pass, is assumed, right? So now what is the probability that it will pass the small t after this t naught? So basically that becomes the probability. This reliability becomes probability. It's a conditional probability. What is that probability? The time to failure is greater than t naught plus t, right? So capital T naught will pass. So now after that small t, will the time to failure pass this small t after t naught? So the time to failure is greater than t naught plus t, given that it will pass t naught. So that's the probability, right? So that's this reliability. The probability of t greater than t naught plus t given t greater than t naught. Now this is a conditional probability, and how is it defined? So it is probability of t greater than t naught plus t and t greater than t naught, right? So probability of that intersection. But if t greater than t naught plus t, then t greater than t naught is already part of it, right? So it's a subset, and so in the numerator you will be having only probability of t greater than t naught plus t. In the denominator you will be having this events probability. So probability of t greater than t naught. So this is your conditional reliability. Now what is probability of t greater than t naught plus t? By the definition of reliability, it becomes reliability of t naught plus t, and the denominator is reliability of t naught. So basically reliability of t given capital T naught is nothing but reliability of capital T naught plus t divided by reliability of t naught. Now what is reliability of t naught plus t? We have found a relation for reliability using Hazard function, right? So using that we can rewrite it as e raised to minus integral 0 to the time. What is the time here? T naught plus t into lambda of the Hazard functions integral, basically from 0 to the given time Hazard functions integral, negative of that, negative exponential of that is your reliability of t naught plus t. Same way we have a similar form for reliability of time t, reliability for time t naught, right? So this is that reliability. So it's basically e raised to a by e raised to b kind of thing. So it's e raised to a minus b, right? So e raised to, so that minus is common, so that we are taking outside. Then so this is your a and this is your b, right? So that minus commonly we are taking outside. So what remains? Integral 0 to t naught plus t lambda of u du minus integral 0 to t naught lambda of u du. Now t naught plus t is bigger than t naught, right? So small t is greater than 0, right? So you are basically having this integral, you can split as integral 0 to t naught, and that will cancel with this minus part. Remaining is the integral coming as a result, right? So integral capital T naught to capital T naught plus t lambda of u du, negative exponential of that is your conditional reliability, right? So it is the reliability of t given capital T naught. So this for conditional reliability also, you are using Hazard function. We have a formula, or we have got a relation between Hazard function and the conditional reliability. Now so this is for generally any whatever be your density function for time to failure, we have this general relations. Now consider say the time to failure. So time, basically we use time is a continuous random variable. So which of the distributions we usually use? Exponential is one of the most commonly used type of distribution for time kind of applications, right? Where the random variable is time, mostly we'll use exponential distribution. There are other continuous distributions also we'll make use of. So if your density function is actually the exponential distribution, it has a form like this, right? Lambda e raised to minus lambda t, where this lambda is not the Hazard function, it's a parameter here. So that parameter we have been using before also, that's why this lambda is used here. Instead of lambda, maybe we can use something else here, because the Hazard function also has the same notation. So lambda it is not the hazard function, it's a parameter of this so this lambda, we say consider maybe instead of lambda say let's take alpha or something. So alpha is the parameter, right? So in that case we'll have the density function is alpha e raised to minus alpha t, where time t is a time parameters, t is greater than or equal to 0, alpha so t is the variable, it is greater than or equal to 0, time variable is greater than or equal to 0, and alpha is the parameter here, only one parameter for exponential distribution. Now what is the reliability function? By definition it is probability of the random variable capital T greater than the input time small t, right? So it is integral t to infinity alpha e raised to minus alpha t dt. Now if you integrate, you will be getting what? So alpha is a constant, right? So e raised to minus alpha t will give you minus 1 by alpha and e raised to minus alpha t. So that minus is here, and alpha get cancelled. So alpha is non-zero, assumed to be non-zero and positive, right? So alpha is positive. So you'll be getting minus e raised to minus alpha. So t you'll be having u, dummy variable. So minus e raised to minus alpha u from t to infinity. So when u tends to infinity, you'll be getting 0. When u equal to t, you'll be getting e raised to minus alpha t minus of that. So since it's a lower limit, another minus will be there. So you'll be having e raised to minus alpha t as the result. So reliability is for this particular density function. The reliability is e raised to minus alpha t. Now what is the hazard function? It is the ratio of density function to the reliability function. So both are probability functions. So density function is alpha e raised to minus alpha t, and reliability function is e raised to minus alpha t. If you take the ratio, it is e raised to minus alpha t, it will be always greater than 0 for any t. It is greater than 0, so they cancel and you will be getting alpha. Okay. And what is the mean time to failure? It is basically the mean of the random variable, right? It's the expectation of the random variable. So the random variable has having exponential distribution. Instead of lambda as a parameter, we have used alpha, because this lambda now it is used for a hazard function. To remove the confusion with the notation, we have used alpha here. So with lambda as the parameter for an exponential distribution, we know mean is 1 by lambda and variance is 1 by lambda square. So here the parameter for the exponential distribution we have taken as alpha. So the mean is 1 by alpha and variance is 1 by alpha square. So mean time to failure, the time to failure is a random variable here, and it's having the exponential distribution. So mean time to failure becomes 1 by the parameter of the exponential distribution, which is 1 by alpha now, right? So the mean time to failure is 1 by alpha, variance of time to failure, it is 1 by alpha square. Now what is the conditional reliability for the time t, small t, given that time t naught is the wear-in period or burn-in or this warranty period. So that is we know its relation as it's the reliability of t naught plus t divided by reliability of t naught. This relation we have already established. So now what is this reliability of t naught plus t? Reliability for any time, it is e raised to minus alpha t. So this becomes what? E raised to minus alpha into what is the time here, t naught plus t, divided by e raised to minus alpha t naught. Now if you divide them, this get cancelled, e raised to minus alpha t naught get cancelled, and what remains? E raised to minus alpha t. So that is your conditional reliability. So this way, for a particular distribution, now we can find what is mean time to failure, what is hazard function. So for a particular distribution of the time to failure, we can find the reliability function, hazard function, mean time to failure, variance of time to failure, and conditional reliability given t naught is the burn-in period or the warranty, right? So now for another distribution, a conditional distribution, variable distribution we are taking, for that also now we can do the same thing. Okay, the standard formula, standard distribution function, standard like representation of the distribution function of variable distribution we have seen is this. The alpha with two parameters it is there, so alpha beta t power b beta minus 1 e power minus alpha t power beta for t greater than 0. This is the standard form we have seen. So now we can use another alternate form here. You take alpha equals 1 by theta power beta. Okay, so if you make the substitution, alpha equals 1 by theta power beta, will be getting an equivalent form like this. So yeah, so alpha is 1 by theta power beta, so you are having theta power beta, so 1 theta we keep with beta, right? The remaining beta minus 1 thetas we keep with t, so we'll be having t power beta minus 1 by theta power beta minus 1, which is t by theta power beta minus 1, exponential minus alpha t power beta. Now alpha is 1 by theta power beta, so that 1 by theta power beta combines with t and you'll be having t by theta power beta. Okay, so alpha is positive, which makes theta also positive. So theta positive, beta positive, t greater than equal to 0. So this is an alternate form. Now it's having some application, and they are called, this theta is now called scale parameter and beta is called shape parameter. So we have the standard distribution function representation for variable distribution is this. If you make the substitution, if you make the substitution alpha equals 1 by theta power beta, and then we have an alternate form like this. Now with this, what is the reliability? Okay, so that is found here. So just basically it's a probability of t greater than t, so it's integral t to infinity of the density function, right? So this is the density function you are having, integrate, right? So now take a t by theta whole power beta as x. Okay, so in that case the reliability ultimately you will be getting 0 raised to minus x. So okay, if you are taking this as x, so ultimately you will be getting, what is x? It is t by theta power beta. So substitute it back, so you'll be having exponential of minus of t by theta power beta. So yeah, so just you have to take the integral. So just check that with this integral, so the corresponding change in limit also will be there. Okay, now what is the hazard function? Hazard function is the ratio of density function to the reliability function. So if you take, this is the reliability function, e power minus t by theta power beta, and you have the density function here. Take the ratio, you'll be getting whatever is cancelling with remaining whatever is a function, whatever is a part of a function, whatever remains, it is this beta by theta, t by theta power beta minus 1. And mean time to failure is the expectation of the random variable which follows this variable distribution with parameters beta and 1 by theta power beta. Now, so with that, what is the corresponding, we know the mean time to failure, what is the or mean of a variable distribution with alpha and beta parameters, what was it? So substitute the, instead of alpha you just use what is that, 1 by theta power beta, you will be getting equivalent, so mean as well as variance. So this is just that. Now what is the conditional reliability? So again, reliability for t naught plus t divided by reliability of t naught. So you have this reliability as this function, exponential this function. Just take the ratio, you'll be getting this result. So for any corresponding distribution function, you can now find what is the reliability function, what is the hazard function, what is the mean time to failure, what is the variance, and what is the conditional reliability. That's the that's what we are doing here, right? So in this two, so for some special distributions, finding it. Now problem, you are given the density function as 200 by t plus 10 the whole cube. T is the time, so t is greater than 1. So it is the time to failure for some gizmos, there for use widgets or something. So now you are asked, so you are given the density function basically. Time to failure, what is the density function is given. You are asked to find what? The reliability function, right? So reliability function is asked to find, and for the first year, so it's in years, is the time to failure is given in years. So for first year of operation, what is the reliability is asked? Basically for t equal to 1, what is the reliability is asked. Okay, time to failure capital T, it is in years for each value. So t equal to 1, the corresponding probability of time to failure we are getting here, right? So 1 you will be substituting, you can get that. So that probabilities are getting smaller and smaller, right? So yeah, for first year the probability that time to failure is 1. What is that? 200 by 10 cubed. So basically 0.2 is that probability, right? So yeah, so you can find those probabilities as well. Now you are not what you are asked is what you are asked to find is the reliability function, and for the first part reliability function and reliability for first year, or t equal to 1, small t equal to 1, what is for t equal to 1, what is the reliability? You are finding the general reliability function r of t, and you are asked to find the reliability, that probability for t equal to 1. Now mean time to failure for this density function, what is the mean time to failure? And we are asked to find what is the design life for reliability 0.95. Okay, so basically for getting reliability equal to 0.95, what is the time? So r of t equal to 0.95 for which t? That's also asked here. That's what is asked in the part. Now part D is asking if 1 year burning period or warranty period is given, will it improve the reliability in parting? So if this burning period is or warranty period is introduced, capital T naught equal to 1, in that case, so this is kind of a conditional reliability, right? So T naught equal to 1, in that case for T equal to 1, is the reliability more than the reliability before? That's what is asked. So is it improving the 1 year reliability? If it is improving if 1 year burning period or warranty period is there? So that's what is discussed here, right? Or that's what is asked here. So first part is asking us to find the reliability. What is the reliability? It's the probability of the time to failure is greater than the variable, means the time given, which is small t, right? Probability of capital T greater than t. So that is integral t to infinity of the density function. What is the density function? It's divided by t plus 10 whole cube, right? Yeah. So just input that function, integrate, what you will be getting. So 1 by t plus 10 whole cube, you integrate, so you will be having t plus 10 raised to minus 3 it is. Right, 200 comes out, so t plus 10 raised to minus 3 if you are integrating. So its derivative t plus 10, its derivative is dt, or the differential is dt only. So basically you can just take the integral, right? So t plus, so if it is t raised to n, then t raised to n plus 1 by n plus 1. So instead of t you are having t plus 10, so t plus 10 raised to n, instead of n you are having minus 3, so minus 3 plus 1, so minus 2 divided by minus 3 plus 1, which is minus 2, and that minus 2 and 200 will give you minus 100. Now t plus 10 raised to minus 2 is there, that becomes 1 by t plus 10 whole square, so minus 100 by t plus 10 whole square, t to infinity. So instead of t you could have used u here, so a dummy variable, so the limit is having that variability, so that's why you should have used a dummy variable u, could have used that, so that's better. So now t to infinity, so if you give the upper limit, it is denominator is going to 0 and numerator is a constant, so that part is going to 0. Now when you give t, you will be getting t 100 by t plus 10 whole square, that minus, and the since t is the lower limit, that 2 minus will give you plus, so 100 by t plus 10 whole square, that is the reliability. Now we got the reliability function. We want to find for time t equal to 1 what is the reliability for 1 year, what is the reliability? So basically substitute t equal to 1 in the general reliability function, you'll be getting that probability. So 100 by 1 plus 10, 11, so 100 by 11 square, you'll be getting 0.8264. So the how reliable is the product, whatever it is lasting for 1 year. What is the reliability? So 82%, 82.64 probability is that 82.64% probability is there that the product lasts more than 1 year. Okay. Now what is the mean time to failure? There are different formulas you can use. It's expectation of t, but we have an alternate formula. We have found that it's equal to the total integral of the reliability function, and the total integral now is only from 0 to infinity because it's a time variable, right? So 0 to infinity r of t dt. Now what is that? So what's the reliability function we got? What is the reliability function? Reliability function we got is 100 by t plus 10 r square. So you substitute that. So instead of you substitute our reliability function and take the integral. So t plus 10 all square, t is the denominator, so yeah, t plus 10 raised to minus 2, so minus 2 plus 1 in the power, and minus 2 plus 1 you are dividing with that, so that's minus 1, so that minus is coming here, minus 100 into t plus 10 whole power minus 1, that is divided by t plus 10. So 0 to infinity, again if you give infinity, that goes to 0. When you give 0, you are getting minus 10, and there is a minus for the lower limit, so it's 10. So 10 years is the mean time to failure. It's in years, the units is in years, so that's why years. So mean time to failure, it is 10 years. Okay, the mean of the random variable t, where t is the time to failure. If it is following this particular distribution function, the density function, the probability function is this, then the corresponding mean of the time to failure, it is 10 years. That's what you are finding. Now you are asked to find the design life to get a reliability as 0.95. So basically that the product should last for when it lasts for the design life, your corresponding reliability should be 0.95. What is the corresponding design life is asked. So this is the reliability function. In the reliability function, you want to find what is the time that gives you, or the product's life. If it is this t, you will be getting the corresponding reliability as the that value. So you are asked to find for 0.95 as the value for this reliability, what should be t. So 100 by t plus 10 whole square, that's the reliability function. This is equal to 0.95 for which t. So you are denoting that as td here. So you solve for td here, right? So yeah, so 100 by 0.95 is td plus 10 whole square. Now take the square root, subtract 10, you'll be getting 0.2598. Here is the td. So now so this is the fraction of year. So what fraction of year it is, right? So in days, how to say it? So 1 by 365, whatever value it is 1 day, right? So this into 0.2598 will give you how many days it is. If you calculate, you will be getting approximately this is equal to 95 days, right? So 1 day in 365 days, or in a year, the 1 day represent the corresponding what fraction, right? So yeah, not into, here it's not into, it should be divided by, right? So this fraction you are having, so how many days it is you are converting, right? So shouldn't be multiplied by, so it should be 0.2598 is the time you are getting in years. So this divided by, you are converting years into days, so you are dividing by the fraction which represent days in a year, a day in a year, to obtain how many days it is there, how many days is represented by this particular fraction. So it's 1 by 365 you are dividing with, you'll be getting 94 points of this, which is 94.9, more than 94.5, so you'll be taking that as 95. Now the last part is asking the reliability if a burn-in period is introduced. Capital T naught is equal to 1. In that case, what is the general reliability function if capital T naught equal to 1? Then you have to find for the time small t equal to 1, what is the corresponding reliability if capital T naught equal to 1. So that general conditional reliability will first find, then for we will substitute small t equal to 1 in that. So that is the reliability if a burn-in period or warranty period of 1 year is introduced. Now we want to compare it with the already non-reliability for 1 year without this burn-in period. That we already know is 0.8264 we have evaluated. We have to check whether the new reliability for reliability of small t equal to 1 given capital T not equal to 1. Right, that conditional reliability, is it more than this? In that case, introducing this warranty period, it's improving the reliability, right? So yeah, so that's what you want to do. So reliability of t given capital T not equal to 1 is what we know that it's equivalent to reliability of t plus capital T naught, which is 1 here, divided by reliability of T naught, which is 1. So reliability function we know it is 100 by t plus 10 whole square. That's what we obtained, right? Now in that, instead of t, you substitute t plus 11, sorry, t plus 1. So 100 by t plus 1 plus 10 whole square, that will be right. So 100 by t plus 10 whole square. So in that, instead of t, you are substituting t plus 1. So you will be getting 100 by t plus 11 whole square. That is reliability for t plus 11. So divided by, that is reliability of function for 1. Function value for 1. It is 100 by t plus 10. T is 1. So 1 plus 10. So 11 square. So what you are having? So this 100 cancels. This divided by 11 square goes to the numerator, 121 divided by t plus 11 whole square. That is the conditional reliability for capital T not equal to 1. Okay, so if the warranty period is 1 year, then the reliability is this. Now, you want to check whether the conditional reliability will be more than the actual reliability without the burn-in period reliability. So we want to check whether this is true, right? So if this is true for all t, then we can say yeah, this is true. The introducing this warranty period or burn-in period improves the reliability. So if this inequality is satisfied for all t, that's what you want. Or for whichever t it is satisfied, you can say for those t, the reliability is improved, conditional reliability is more than the actual reliability. So r of t given 1 greater than r of t for which t, that's what we want to find. If it is for all t, then we can, for all t you can say this reliability is improved. So 121 by t plus 11 whole square is conditional reliability, this conditional reliability. So is this for it greater than r of t, you will be having this inequality, right? 100 by t plus 10 whole square is r of t, that we have already found. Now from this inequality you will be getting 100 by 121, which is, yeah, so t plus 10 whole square, take to the other side. So this is a perfect square, this is also a perfect square. Now take the square root, time it is, so negative is not used, negative, the other side inequality is not used. So t plus 10 by t plus 11 is greater than 10 square by 11 square, this is, so it will be 10 by 11, right? Now you multiply, cross multiply, you will be having 11t plus 110 is greater than 10t plus 110. So 110 get cancelled and you will be getting 11t is greater than 10t. So t is greater than equal to 0. So for every t it is true, right? So 1 year burn-in period will improve the reliability. Now what is the reliability for 1 year if this burn-in period is there? So it will be 121 divided by t plus 11 whole square. Instead of t you substitute 1. So the value you are getting is 0.8403, and reliability without this burn-in period for 1 year it was 0.8264. So this reliability is more. So it's for 1 year also we are finding that the reliability has increased. Okay. Now so now you are given the hazard function, and another problem, the solid state power unit has a hazard function, or the instantaneous failure rate function. Hazard function is also called. That rate function, it is this 0.003 t by 500 the whole power 0.5 for time is positive. Now you are asked to find the reliability function if the power unit must operate continuously for 50 hours. So reliability function value at t equal to 50, at reliability for 50, time equal to 50, that's what is asked to find. Now we can find if the hazard function is given. You know, hazard function is the ratio of density function to the reliability function, and equivalently we have found, solving that differential equation, we found the reliability function is exponential of minus integral of the hazard function, right? So integral 0 to t, right, of that hazard function, and the density function is the differential of that, so it's we got as lambda t into e power exponential of minus integral 0 to t hazard function. That's what the relations we had, right? So yeah, the relations we already know, right? Yeah, these relations we already know. Yeah. So in that case, how to solve this problem? We are given the hazard function, then we can find the reliability and density function also. Right. Once you know the reliability function, we can find mean time to failure error. So here first you are asked to find the reliability for 50 hours if this is the hazard function. Now determine the design life if for a reliability of 0.90. So what should be the time which gives reliability as 0.90? So find the reliability function, general reliability function, equate it to 0.90, find what is t, solve for t. So that's your design life for a reliability 0.90. Now once you have the reliability function, you can just to find the mean time to failure, you can just take the integral of the reliability function. Now given that the unit has operated for 50 hours, so it's a conditional probability, right? So t not equal to 50, what is the probability that it will be it will survive a second 50 hours of operation? So probability that small t equal to 50 given capital T not equal to 50, that's what is asked in this part, conditional reliability. So this is the hazard function you are given. Now let's find the reliability. It's e raised to minus integral 0 to t hazard function, lambda of u du. So the function is 0.003 t by 500. So you use the dummy variable here, so u by 500 du. So once you integrate, you will be getting such a function, right? Okay, so the u is not required there. Is of yeah, it's required, u is required. Okay, now so this is before giving the limit, so 0 to 50, yeah, exponential of this is integral is in the exponential, right, in the power, right? So yeah, so you take the integral, give the limits, right? So you directly have to find for 50, so that's why the upper limit is given as 50. Instead of that, you can directly find, you can find the general reliability function, keeping t itself, you can find the reliability function. Then ultimately, finally you can give, instead of t equal to t, you can substitute 50 and find the reliability for 50. That also is okay, right? Now and if you are doing that, then for the second part it will be easier, right? So you are finding the general reliability function and solving for the time for 0.9, right? Reliability, 0.9 reliability. So that's what is done in the next part. So reliability for 50, you can just exponential of this integral, instead of t you are substituting 50, or just find the general reliability for any t if this is a hazard function. So in terms of t something you will be getting, substitute t equal to 50 there, you will be getting the same value. Now TD not equal to 0.9, you want to find what is the TD for reliability equal to 0.9, right? So reliability of TD equal to 0.9, what is this TD? This is what's asked. So what is the reliability for the time TD? It is e raised to minus integral 0 to TD of the hazard function. This is the hazard function, right? So with respect in variable u, I'm giving that. Now take the integral the same way, right? You'll be having, you just solve this, that's it. You solve and you'll be getting ultimately 111.54, and the units here, it is it's hours, right? So we are having hours. So this is given in hours, 50 hours, and so the units is hours. Whatever you're getting in hours here, having the result. So it's time to fail. So the time to design life, or the time to failure, if it is 111.54, then the corresponding reliability will be 0.9. So for 0.9 reliability, you want this design life. At least this should be the design life. Okay, time to failure should be at least this, and should be this for 0.9. Yeah, if it is more than this, then reliability will be more. So now mean time to failure we want to find here. So we know the reliability function is this. Just take the integral of the reliability function. What is the reliability function? Exponential minus integral 0 to lambda of u du. Just take the integral of integral 0 to infinity of that, you'll be getting. So this is basically, so consider the constants together, and yeah, just integrate. While integrating, yeah, the power is t power 3 by 2. So while integrating, you have to make some substitution. So once you make the substitution as x equal to the constant t power 3 by 2, the integral transforms into a, or it looks similar to, it becomes a, it can be identified as a gamma integral, right? So and that's what is done here. So yeah, ultimately that gamma value, if you find, you'll be getting the value of mean time to failure. It is 451.65 in units. It's in hours. Now the second part is asking you to find the probability of small t equal to 50 given capital T not equal to 50. So that, so the so the reliability of t equal to 50, small t equal to 50 given capital T not equal to 50. This is what is asked. So what is this? It is the probability of so after t naught passed, what is the reliability of t equal to 50? So the probability of your capital T, the time to failure, is greater than t naught plus t. Now what is t naught plus t here? It is 50 plus 50, 100 given yeah, given t naught is 50, right? So t naught is 50 means the the condition probability is basically the reliability for t naught equal to 50 means the corresponding time to failure is greater than that t naught, right? So this conditional probability is what your conditional reliability is, and this becomes t naught plus t becomes 100. So t greater than equal to, so this is your probability of t greater than equal to 100 given t greater than equal to 50. Now this conditional probability is nothing but reliability of 100 divided by reliability of 50. That equivalent formula we have. Now this we got the result. It is equal to exponential of minus integral t naught to t naught plus t lambda of u du, right? So that we are using here, and with small t equal to 50 and t naught equal to 50, you will be having integral t naught to t naught plus t. That becomes what? T naught is 50, capital T naught plus small t now becomes 50 plus 50, which is 100. So exponential minus integral 50 to 100 lambda of u du. This result is what we have, like in hazard function we have found that. So this is the conditional reliability. That's what we are using here. So we got this. Right, what is it? Yeah, now just find that integral and the exponential value. That's it. Integrate the hazard function. Hazard function is given to us. Just integrate the hazard function, give the limits. Now you'll be getting exponential or something. Find the value of that exponential. That is the corresponding probability. You'll be getting 0.9438. So this is the conditional probability that your product lasts at least 50 units or 50 hours, or 50 hours, given that its warranty period is 50 hours, or burn-in period or wear-in period is 50 hours. That's it. Okay, now this part, another problem, a manufacturer determines that on average a television set is used 1 hours per day. Okay, so mean usage. So the expectation of so average usage is 1.8 hours per day. It's not time to failure or something. It's average usage is 1.8 hours per day. Now a 1 year warranty period is offered on the picture tube. So the capital T naught is basically given here, right? So warranty period it is given. So and the picture tube is having a mean time to failure 2000 hours. Okay, so mean time to failure is given to expectation of the random variable time to failure, it is 2000 hours. That's given to us. The 1 year capital T naught equal to 1 year. So 1 year corresponding hours, that's the year warranty period that is given to us. Okay, now 1 year 1 year warranty is offered, means for the usage of 1.8 hours per day on average, that only warranty is offered. So it's not 365 into 24 hours. So in per day 1.8 hours only it's expected to the television set is expected to be used, right? So it's not 24 hours. So the warranty is not when we use it for 24 hours, it's when we use it for 1.0 hours on average per day, right? So the corresponding hours will be the warranty in hours. So 365 into 1.8 hours will be the warranty in hours. So that is there, right? The warranty period in hours, it's known to us now, 365 into 1.8 hours. The mean time to failure, it is 2000 hours. Okay, now that is also known. So if the distribution is exponential, the time to failure is an exponential distribution, that random variable is an exponential distribution. Now you are asked to find what percentage of the tube will fail during the warranty period, right? So during the warranty period, which means 1 year, what percentage of the product or the TV picture tube will fail? That's what's asked. So since it's an exponential distribution, we know for an exponential distribution we have already found what is the reliability function, right? It's e raised to minus the parameter into t. So the parameter, now let's take lambda itself. Okay, so so lambda itself, let's take instead of alpha previously. What was our hazard function there? Hazard function, actually it was, you are getting it as alpha basically. If you instead of alpha, if you use lambda, and that makes sense, right? So in this particular case, that lambda itself, if you are using, that won't be an issue, because lambda of t you are getting as lambda itself for exponential distribution, or lambda of t equal to that parameter. So so it's for any t it's a constant. So instead of alpha, instead of changing it to alpha, you could have used lambda. Also makes sense, means there won't be confusion. So if it is not equal to lambda, then only there will be much confusion. So so if lambda is used, still it will be making sense. R of t is 0 raised to minus lambda t or alpha t, whatever. So that is your reliability, right, for an exponential distribution with parameter lambda. In this case, let's take lambda. So lambda is the failure rate, or the parameter is the failure instantaneous rate of failure that we found for an exponential distribution. We have derived it already generally, right? So now mean time to failure, it is given 2000 hours. The units is hours, so 2000. Now what is the mean time to failure for an exponential distribution? Is 1 by that parameter of the exponential distribution, so 1 by lambda. So 1 by lambda is 2000. So the failure rate is not given to us, but the mean time to failure will provide us what is the failure rate. So lambda is 1 by 2000, you will be getting 0.005 per hour. Now the probability of your time to failure is less than or equal to 1 year will give you in as a percentage, it will give you what is the corresponding part of the picture tube that's failed, right? That's basically the idea here. So probability of t less than or equal to 1 year. Now 1 year, the in hours you are having the units you are having here is hours, so 1 year will convert into hours, and the usage of TV for in hours for that period given to you. It's 1 year given to us, and in 1 year per day 1.8 hours, 365 days we are, basically 1 year is 365 days, and it's not 24 hours we are using the TV set. It's not expected to be used for 24 hours, it's for 1.8 hours. So what is the usage expected? It is in 1 year, it is 365 into 1.8 hours. So yeah, so the probability that the time to failure is less than or equal to this, whatever percentage you are getting, that corresponding percentage of the picture tube is failed. That's what our conclusion will be. That's the way we are doing it, this. So probability of t less than or equal to 365 into 1.8 hours. So now what is this? 1 minus probability of, using reliability. Since we know the reliability function, that's why you are using this corresponding complement probability. So it's 1 minus probability of t greater than whatever this is 657 you'll be getting. 1 minus reliability of 657, and we know the reliability is c raised to minus lambda. It is just substitute 657 in that, lambda with lambda equal to 0.005, you'll be getting 0.28. So then we'll say 28% of the tube will fail during the warranty period. This is the idea.